Welcome to my video lecture. Today we are going to discuss about enzyme kinetics. Let's start the class. So, enzyme kinetics. What is kinetics? So, kinetics talks about the speed of the reaction. Right. So, how to calculate the speed of the reaction? For example, you are performing a reaction, let's say a chemical reaction. So, a chemical reaction, your substrate A is converted to B. So, this reaction, if I want to calculate the speed of the reaction, what type of experiment that I have to follow? So, the experiment like this. So, what you do is you take a time interval. The time interval, say every 1 minute you are checking how much substrate is converted into a product. So, what you are estimating the amount of product produced. Here the product is nothing but the B. Say at the start of the experiment, 0th time, so this is minute. At 0th time, you don't have any product. So after 1 minute, you have your product is say 5. After the second minute, your product size is 10. Say after third minute, your product size is 15. So now you calculate the delta P, that is the change in the product concentration. So this is 5. So if I am calculating the next minute, again delta B, this is 5. So again the same thing, repeating 5. So from this experiment, what we have come to a conclusion that at every minute, your delta P is changing 5 per minute. So this is the speed of the reaction, right? So this we also call rate of reaction, right? So the rate of reaction calculated like two ways. One, how much product is produced, that is change in product concentration, that is delta product with delta T. So here as you see in this example, so at every 1 minute how much product is changing. So this, if I am putting it in a mathematical way, I can write it in a differential equation form. So dP by dt. So the rate of, so there is another way to check this. The delta substrate again with respect to delta T. So here the substrate is, according to this reaction, the substrate is converted into a product. So if I am calculating how much, say here 1 mole of substrate is converting into a 1 mole of product. So if I am calculating how many moles of substrate, say for example 5 moles of substrate is consumed per minute. So that 5 moles of substrate is only changing into a product. The same way, we are calculating the rate of reaction as a substrate consumption per respective time. So if the 5 molecule of product produced, same thing 5 molecule of substrate is consumed. So this can be written in a mathematical form, that is in a differential equation form, ds by dt. But you need to include a negative sign. Why negative sign? The negative sign is indicating that the substrate is reducing with respect to time. So that's why we are including the negative sign. So the rate of reaction is symbolized in a normal chemical reaction, it is mentioned as R, whereas in an enzymatic reaction it is mentioned as V. So both the symbol is used in a book. If you come across the book, both symbol is used. So this is the rate of reaction, right? Now we will see how this rate of reaction can be calculated from the stoichiometric equation, right? That is the next thing. So we are comparing the how this rate of reaction vary with respect to the chemical reaction and with respect to the enzymatic reaction. So we will going to compare a chemical reaction with enzymatic reaction. So let me start writing the stoichiometric equation, the same equation as we mentioned in the previous thing. See here, A is converted into B. So this is a chemical reaction. How the same reaction happen when in the presence of enzyme? Here A is binding to enzyme, then it's form a enzyme substrate complex, then it's converted into a product. So how to calculate the rate of reaction for a chemical reaction? Say R. How it is depends on that. So if I want to calculate R, I should know how the correlation between your substrate and product. So for that, so if you draw a graph, what is the graph? The graph between the product concentration, sorry, this is not a product concentration, this is a substrate concentration, because always the x-axis should be a independent variable. So here the independent variable is substrate, so that is a substrate concentration, and your y-axis is a product concentration. If you correlate these in a chemical reaction, you may expect a line like this. What is this line? This line is a linear relationship, and this slope of this line is always a constant. So according to this, what we are inferring from this, when the substrate is increased, so here the substrate is nothing but A, so here I am mentioning substrate concentration increase, that is proportional to the product concentration. So as long as the substrate is available, there is a product, there is no variation. If you want to increase the more product, so I have to include more substrate. But when it is come to the enzymatic reaction, will this obey the same way? So if I am drawing a graph between the same A versus B, same like this. So both the reaction is the same, only difference is here there is an involvement of an enzyme. So what I am expecting is, actually the scientists who are first time investigate many reaction, enzymatic reaction, they are expecting similar type of curve like a chemical reaction, non-enzymatic reaction. When I say chemical reaction, I should say that this is a non-enzymatic reaction. But what they have observed, instead of getting a straight line, they got something like this. So what it means, even increasing a substrate beyond a point, say this is the point. So beyond this point, so this level, the product is not producing much more higher, that is after this point the same level of, so this is the maximum product is produced. After that there is a saturation. What is the word? The word is saturation. What I mean by saturation, after that the product concentration is not increasing, even though I am increasing the substrate. Why this happens? What actually saturates? Here, according to this experiment, this reaction, even though I am increasing your substrate concentration, but there is no further increase in the enzyme concentration. Whatever the enzyme that you have added in the very beginning of the experiment, that maintain constant. As you know that enzymes are reusable, so once the reaction is done, the same enzyme is use it again. So the enzyme concentration normally present in a limited quantity. So here the enzyme concentration is constant. So even though the enzyme substrate concentration is increased, there is no sufficient further increase in enzyme. So there is no sufficient enzyme to support. So there is a saturation. So I will put an example like this, right? If I am taking so if I am taking an example, say I am taking a enzyme substrate is, say I am increasing from 50 molecule to 500 molecule, but the enzyme molecule is only 50. So at this point, this is, you can say this point is 50, right? This is 50. So even if I am increasing from 50 to, may say this is 500, even I am increasing from 50 to 500, there is no enzyme more than 50, so it is saturates. So here the enzyme is the limiting factor. So if I am calculating, so you can understand what is the saturation, and if I am calculating the order of reaction. So what is the order of reaction? Order of reaction is nothing but how many variables that affects the outcome of the experiment or reaction or process. Here the variable here is in a chemical reaction or non-enzymatic reaction, you can see the order of reaction is a first order. Why? Because here the only variable that affects the conversion of B is concentration of A, provided no other factors influencing. So according to the example, there is no other factor influencing. So this is a first order. So the entire reaction is a first order. So if I am calculating R, so here if I am calculating R is nothing but is proportional to only your A. So from this, if I am calculating R is equal to, so if I am including a rate constant, say K into A. So if the rate of reaction calculated, R is equal to K into A. So according to this, if A increase, R is increase. But if I try to use this formula in this enzymatic reaction, this will not happen. The reason here, this is not this, if you look at this if you look at this equation, this particular graph, this graph says it is not only a first order reaction, it is a combination. So look at this place, this part means this entire part, whichever I shaded now in blue. This blue, according to this point, the saturation, until the saturation arrive, so the reaction behaves like a normal chemical reaction without enzymes. So it follows a first order. Whereas once the saturation happens, then it's become zero order reaction. Why? Even though if I am increasing the A, that is the substrate concentration, after saturation there is no further increase in the product concentration. So the rate of reaction has become constant once the saturation is achieved. So there is a two-way, there is a combination of both first order and zeroth order. So the normal, this particular equation, the normal rate of reaction equation is not obeyed by enzymatic reactions, right? So now how I can check this? So that is what we call a real enzyme kinetics. That's how the enzyme kinetics is varied from your normal non-enzymatic chemical kinetics, right? So we need a special look in special models to explain this particular graph. So that what we are going to see next.